Hello. I think it's okay, we can start. We are 121 in class now, and we are also live on YouTube. So others who prefer to join us from YouTube can do so. And if your colleague is not here, you can alert him or her that we have started the session. So today we are going to talk about exploratory data analysis. Before I begin the talk, I think I should share my screen because I'm going to talk some of the things the notebook directly. Okay, so I wanted to make the presentation a little bit formal. So I have this guide to kind of help us streamline the presentation. Okay, so Python for management accounting exploratory data analysis. Already we have gotten the understanding that the management accountant's job for today's businesses is so much about data. And because businesses now generate big volumes of data because of factors like digital technology, the proliferation of digital gadgets, and the availability of technologies for us to handle data. Hello, can you hear me? Hello, if you can hear me, you can hear me, okay?
Yes.
Okay, that's. I wanted to be sure if everything is right before I proceed. So now let's continue. I was saying that we all understand the job of the management accountant in today's businesses. It's purely about data handling. And by that, the management accountant needs to get skills about how to analyze big data. And that's why we are doing these kind of things. Python can never be excluded. Okay. So with that said, major part of the management accountant's job, as far as handling data is concerned, will be to get a sense of what each data represents, get familiar with what the data set represents. For example, take yourself as a management accountant, and I have given you data. So take it like that is your business, a data from your business. For now, you have little and sometimes no idea about what is really contained in the data, what the data really looks like. Of course, you can get some sense from the name, car sales data or something like that. So you will get that first-hand impression that, okay, this is about cars. But apart from that, you can't know exactly the details of the data set. Whether the data set is very, very big, whether it's a medium-sized data or small. How many columns are in the data? What are the column names? How many rows are in the data? And so on and so forth. Okay, so that's what exploratory data analysis does. I don't want to quote any formalized definition. Okay, so exploratory data analysis is all the things that you have to do to get acquainted with the data set, to get very familiar with the data set, so that you'll begin to think of, okay, what hypothesis can you draw from the way you understand the data, and which maybe statistical modeling is more suitable for the data. It is when you have understood all the dimensions of the data that those further analysis can be done. So that's what exploratory data analysis is. Okay. So I'll share the notebook with you after the session, but I have some explanation here. I think it can help you. So when you get a notebook, you can go through them. And some of the specific things that we do inside exploratory data analysis. Yeah. Okay, so let me read some of them so that it gives us an idea of what we should expect. I've given the general meaning of it. So these are some of the specific stuff that we'll be doing. Understanding the basics of the data set. How do we do that? I remember I was doing a project within last week. I had to complete it yesterday. And the data set was about 8 million rows. 8 million rows and several columns. So if you get that data set, what will make you understand that this is what you can do on the data set, blah, 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 is after you have done a thorough exploratory data analysis. Then you can think of which models you have to do. Whatever you want to do, you need to really understand what the data represent before you can do that. So understanding the basics of the data sets, EDA starts with getting a basic understanding of the data set. This includes knowing the number of records, the types of variables like numeric, categorical, and a general sense of the data set structure. Okay, so I said it earlier. Summary statistics. Okay, for all the columns in the data set, and some data sets can be very big, having about 60 columns. That's the kind of data I want your statistics teacher, to be showing you for you to be doing. That is no blackboard and calculator and pen issue. So you need to get summary statistics on all the columns in your data set, on all the variables you are studying. What is the count? Okay, that's about the number of rows. What is the mean for each of the column? What is the standard deviation? What is the minimum value? What is the maximum value? And all the statistics that you can think about. You need to do that summary statistics. And that gives you a lot of information about the general structure of the data and some of the issues that maybe that require further attention in the data. Data cleaning, for example, if you have done that analysis, maybe you will see that you need to do some data cleaning. You need to do one or two things. Let me read what exactly we can do under data cleaning. There are so many things you can do, which we will actually demonstrate in this session. Identifying and handling missing values. Yes, if you have done the top part, trying to understand the general structure of the data, you would have realized whether you have missing value issue or not. And if you do have missing value issue, we need to clean the data. In the realms of data science, there's a huge area called data pre-processing. Okay, so that will fall within that side. dealing with missing values, they are all part of data pre-processing to make the data ready for your machine learning modeling. But whether it's machine learning or it's any other thing, you need to identify whether you have a missing value issue and then you clean the data. Any analysis or most analysis will not be well done if you have some data missing in your data set, right? So we'll see how to deal with that. We also have to check for issues of outliers. Some models, for example, regression is very responsive to outliers, and therefore you need to check for the issue of outliers. And if you have outliers in your data set, and if it is very huge, you might have to deal with the outliers as much as the model you need to requires you to deal with it. And we'll see how we check for outliers and the possible ways we can deal with them. And then most importantly, because you want to get an understanding of how the data looks like, including also the relationship among the columns of the data sets, which will give you an idea of what is happening and what model you can do, we need to do a lot of picture showing, and that is visualization. So we need to visualize most of these things. The eye wants to see them in a certain way, so we get appreciation. So visualization is automatically there, and major part of EDA will be visualization. And then as part of the visualization, we also want to see patterns, like I said, the relationships among the columns, which will inform us about what analysis we can do, what hypothesis we can do on the data, and what inferential statistics we can do for which type of inference. Okay, so that's it. When you read the full story that I put here, you get to know exactly what I'm saying. That's exactly what it's saying. Okay, so with that said, with this brief explanation of what EDA is all about, let's get our hands dirty. So now I expect you to have your hands on your laptop's keyboard or any other keyboard. And then we begin to make our hands dirty about how to do EDA. So we will import these usual suspects. They are friends for now. We've been using them almost every analysis that we do. NumPy as NP, Pandas as PD, Matplotlib, PyPlot as PLT, Seaborn as SNS. I think these are the most important ones. The sklearn is a machine learning package. We will not really use it here. And for this presentation, we will not do the prediction modeling. We will do up to the EDA. So we don't necessarily need these packages. But of course, it's the tradition. Since most of the time we will use them now or later in our process, in our modeling process, we sometimes import all of them straightforward so that in case we have to use them, they're available for us to use. So let me run this. So when I run this, forget about these numbers because I was doing them before we started the session. So we have run this cell, which imports the various packages that we need. Then we are going to load the data set. Okay, so now I want to show you something we have not done before. We can load the data straight from the internet. Seaborn has some sample data sets. So the data set I sent to you, I actually saved it from Seaborn's one of the sample data called MPG. So when you want to get a sample data set from Seaborn, after you have imported that package, and we have done that Seaborn as SNS, then there's a method that you can do on SNS. That method is load data sets. So if I do that method on SNS, and that method takes this argument. The argument is simply the name of the data set. There are some number of data sets. I know there is iris. Iris is a data set about flowers, iris flowers. And there is this MPG, and there are a number of other databases there with SNS. So you can put it down somewhere, and then you go and check on the internet. You can simply type sample data types in Seaborn or any other expression which makes sense. Then you get to know, okay, then you can use some of these data sets to do what they call play data. I mean, just play with it to learn. Yeah, let the learning be playing. That's how we learn. Okay, so when I do this, it's going to run, pull this data set, MPG, from the sample data sets in SNS. And I'm going to store that in as data. Automatically, it's going to be a data frame. So as part of EDA, once I have loaded the data, we can check the shape of the data. By shape, what we simply mean is how many rows in the data set, how many columns. That's the shape. That's the shape. So row by column, that's the shape of the data set. And the shape thing here is an attribute, not a method. So, and that's how Python does it. If it is an attribute, it doesn't have this parenthesis. Okay, this is actually for functions. And when a function is working on an object, that function is on the object. So data.shape will give you the shape of the data set. For this kind of data set, it is 398 rows and then 9 columns. Okay, so when you are given this kind of data sets, your calculator and your pen and your exercise book, there's nothing you can do with those tools, actually. So that's not how we learn it. So we can also check, now we know the shape, we can also check the data types for each of the column. But even before the data types, let me do this, I think. Even before the data types, we could have done this. mpgdf.info to know the general information about the data sets. Sometimes this info function will bring anything that you need to know to get yourself very well acquainted with the data sets. And therefore, you might not even need the shape function and other functions. But this session is also a tutorial. So we are doing all of these things. You will see a lot of overlaps. And that's the one of the things beautiful about Python. You can do the same thing in many ways. Okay, so the overlaps you will see in them is important because we are learning it for the first time for you to know the various ways you can do the same thing. So even before the shape, checking the shape, well, we can even ignore the shape thing and do df.info or mpgdf.info, and it will give us every information that the shape thing will give us. So you will see that it's telling us the range index, which is the number of rows, is 338 from the info. And it is from 0 to 397. That is 398 actually. And then we have the data columns, total columns of 9. That's the same thing that the shape is telling you. But this one gives you extra information. Apart from knowing the rows and the columns to be 3, 9, 8, and 9 respectively, it also gives you extra information about the names of the columns. So you see the number 0 and the name here. The first column is MPG. The second column is cylinders. The third column is displacement. The fourth column is horsepower. The next one is weight. The next one is acceleration. The next one is model year. The next one, origin. And the last one is name. And then it also gives you this information. None, no count. What this one means is that this is the count, the number of values under each column. So this is the column and the values under the column. Already, you know that the total data set is 398 rows or entries. So you check here against and that's a gauge of whether you have a missing value under each column or not. So under the MPG, it's also saying 398 non-values, non-null values. So it means there's no null value, 398, 398. And we can see the same thing for all of them. Oh, yeah, 398, 398. Okay, then it also gives us a sense of the data types for each of the columns. So these are the columns and their types. So almost all of them are of the numeric type. Floats is a numeric, int is a numeric. All of them, or 6 of them, 7 of them, MPG, cylinders, displacement, horsepower, weight, acceleration, model year, all of them are numeric columns. And origin and name is of the object type. It means the values under these columns are strings. Okay. We can get sections of the data which the info function is presenting to us from some other codes like this. We can do data.d types. What it means is that data.data types. So the object was actually loaded as data. So we are calling this attribute on the object. D types. This is also attribute. It's not a function. So data.d types will give you for each column name the data type, just like the info function is giving. Okay. Sure. So these are all parts of the exploratory data analysis. But I added this section to it. Since I pulled this information is pulled directly from the internet, from Seaborn, it means it is not on my computer. It's not on my local drive. So when I don't have internet and I run this, it will not work. It means I will not get access to the data. If you have internet all the time, maybe that's not your headache. But we can understand that sometimes we need to work offline. So how do I save this onto my local drive? I've loaded the data. I have seen the dimensions of the data. That's cool. So can I save it so that maybe I'm going home? When I go home, I will not get internet. I will want to work on it offline. You can save this data frame to your local drive by calling the name of the data frame, the object. We saved it as data. And then there is this function in pandas. It's quite very intuitive, to CSV. That's you are converting to a certain format. You are converting to a certain format. And in this case, this is a conversion to the CSV format. It can also be to Excel, to SPSS. Pandas can speak with so many other formats, many formats. You can Google to check the various formats which pandas can read and write to. It's just marvelous. So for this particular purpose, we want to save to CSV. CSV is a very, very portable format where almost every platform it can read. So we prefer to save it like that. So data save to CSV. This is what this broken language, this is like a broken English. The object is data dot to CSV. So convert to CSV, save to CSV. And then it's a function, the to CSV is a function. So you see this parenthesis, and these are the arguments you can pass in the parenthesis. Okay, if it is to save it to CSV on your local drive, what name should be given to it? So that is this first parameter or this first argument. mpg data.csv. That's how I called it. You can call it a different name. And then you can see that pandas automatically, especially if you don't provide row label, it will give you automatic row label, which is 0 up to the size of the data. And when we are saving, we don't want to save those numbers, those row labels 0, 1, 2, 3, up to 397. We don't need it. So you can say index equals false. If you leave the whole of this part of the code off, it means it will save everything, including those index numbers. If that is okay for you, fine. You can save it like that, and later when you are dealing with it, you can drop that column. That's up to you. Okay, so when I run this, it's going to save that. I have already saved it. I've saved it before, so I don't know how it's going to do. Let me see the feedback. Okay. The reason why we are seeing that feedback is because I have saved it and it is the same data that we are actually using. So that's why it's giving me this thing. But for your side, when you do that, it will save to your file. And if you want to check, let me check it here. Before running this code, I didn't have any file like mpg data.csv in my folder. But if you go and check now, it is there. I saved it there. Okay. So once you have saved it, then maybe you may want to begin the work from that saved file so that anything you are doing will be saved on your local file. So we now have to read the data from the source that we saved from the local drive. Okay. And there's a simple function that helps you to read. Read, that's the function's name. So the function's name is a little modified depending on the format you are reading. So if I'm reading CSV, it's read underscore CSV. If I'm reading Excel, it is read underscore Excel. If I'm reading JSON file, it is read underscore JSON. If I'm reading SPSS file, it's read underscore SPSS. It's that simple. So I'm going to read it. This is how I saved it. mpgdf. So for this time, I'm going to call it, I'm going to actually give it an object name mpgdf instead of the data so that we don't have that conflict. When I loaded the data straight from SNS, I loaded it with this name, data. And then I saved it onto my local drive as mpg data. And I'm going to load that mpg data into pandas. I can call it the same mpg data, but here I gave it mpgdf. It doesn't matter. Then you do pd.read. This is pandas. Pandas read CSV file, and the CSV file is this mpg data.csv. But your code can be this for it to work if the notebook that we are using to do this exercise is sitting at the same directory as the file we are reading. Otherwise, you need to copy the full file directory. In your notebook, assuming if you can know where it is somewhere, you can just right click here, for example, and say copy path. And then you put there. Or you can go to wherever the source is, right click. I think in the menu you can see copy path, and then you can copy and put it here. It's as simple as that. Or you can read further on how to do it exactly so that you don't make mistakes. It's not difficult. So we run this, and then we also added that it should show us the head of the data. So that is mpgdf. That's how we saved it. Dot head. So now we can see that apart from all the information we have had, okay, 9 columns, 398 rows, 7, 8, yeah, 7 of the columns from MPG up to model year, they have the numeric type, and there are also string types, columns, and so on and so forth, okay? Apart from that, we may want to actually see the data in some good way, the way we normally want to see it in this way. Okay, so that's the mpgdf.head. In pandas and in Python in general, we frown on the idea of showing all of your data sets. For example, there is a data set on cargo. That data set is normally used to learn about machine learning models. The data size is about, I said I would check it, about 20 million. I think it's about 200 million, 200 million records, 200 million rows. Yeah, that's the size of the data. So such a data, it will be insane for you to want to open the data and see the data, like Excel will want to do it. If you have to open such a data in Excel, maybe it will not open, and you'll be lucky if your machine doesn't even break up. So Python doesn't go by that approach. When you should kind of read that big data into Python, it will read it within a split of a second, and the reason is this. It will read the head and the tail of the data. You don't need to see the full range in between the head and the tail. And the head is just 5 rows of the data. The tail is 5 rows at the bottom of the data. That gives you a comprehension of, okay, this is what the data is about. Of course, you just need the column headings and the nature of the values in the data. So you don't need much to understand that part. So that's the dot head. The dot head by default shows you 5 rows. But of course, you can change the number of rows that it presents. For example, I can put 3 here and drop the 5 to 3. We may also want to visualize the tail. But if you want to do head and tail, this is also a tutorial. That's why I'm breaking things up. If you want to do head and tail at the same time, then you just need to call the whole of the data sets, which is mpgdf. And it's by default give you the first 5 rows, 0 to 4, and then it will bring you this. It means it is collapsing everything in between, and then goes ahead to show you from 393 up to 397, which is the bottom 5. Okay. So that's what you can do to get head and tail is by default. And for tutorial sake, we are splitting it. You can do mpg.tail and you get the last 5 rows in the data sets. That's what. Extracting summary statistics. Now we have had some good understanding of the data for now. We know that 9 columns, 398 rows, the column names MPG, cylinder, horsepower, blah, 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 blah. And the types, floats, ends, objects. That's a good understanding. We can go further to understand some statistics about the data sets. And there is a function in pandas called describe. Actually, descriptive statistics, that's the meaning. And this is more intuitive even than the word or the expression descriptive statistics. Describe the data set for me. Describe. So when we do mpgdf.describe, by default, it will do summary statistics or descriptive statistics on all the numeric columns. It will not do for the object columns or the non-numeric columns. We have 2 non-numeric columns in our data sets in the name of origin. See the values, USA, where the car is coming from. Okay, so maybe let me take the opportunity to describe or explain what the data set represents. I understand we have already done that exercise, but let me just repeat it for emphasis. This is information about some cars that are maybe, let's take it like it's our company. And we have bought the following cars. All of these cars are cars we have bought before. You can take it from any angle, whether we are selling it or we are buying it. But what we want to do is that this column, the MPG column, this column is a measure of the fuel consumption. Or if you want to look at it from the reverse side, fuel efficiency of the cars. So this car, this row represents a certain car. Any other row is for a specific car. So for this car, this was the measure for the fuel consumption, 27. The higher means it consumes more. The lower means it is less, it consumes less. Then we also have some other information about those cars as well. So for this car, we know the MPG, which is the fuel consumption measure. We know the number of cylinders in the car's engine. We know the displacement of the car. We know the horsepower of the car. We know the weight of the car. We know the acceleration of the car. We know the model year. And the car is coming from the USA. The car is Ford Mustang GL. What we want to understand is that this fuel consumption measure, is it influenced in any way by the other characteristics of the car, like cylinders, displacement, horsepower, weight, acceleration, model year, origin, blah, blah, blah. So that is ultimately what we will want to understand. But we will first have to understand the general characteristics of the data set, which can even influence our choice of model in wanting to understand whether the MPGs are influenced by any of these other characteristics. Okay, so that's about what the data set represents. So this is the summary statistics when we run the mpgdf.describe. This is what you see. You see the count. The count will be 398 for all of them, unless, okay, there's a suspect here. But I couldn't spot this one. Let's go to the info outputs. When we were checking for the non-null values in assessing whether there's a missing value. 398, 398, 398, 398, 398, 398, 398, 398. Okay. Okay, so this is when it was loaded from SNS. Okay, so it's something is important here. When we did the describe function on the objects on the data frame, when you read a count statistic, you now realize that we have 392 for horsepower. It means that there are some missing values under horsepower. I think that is coming from the data that we see. And this is even good for us to learn about how to deal with missing values. Okay, so we have missing values, but even before that, let me do this. Let me do the info again on the on the new data frame that we are using, the one that we saved and we loaded. So let me do mpg df.info. And now let's check the columns. Of course, it should be a total of 398 values under each column. So we are coming to check for each column. We can see that under horsepower, we have 392. So it means that for some rows under that column, the value for horsepower didn't come, couldn't find it. And let me actually show you the data sets in Excel so we can actually appreciate what we are seeing here. So let me unshare the screen. Okay, I guess now you can see my screen. Okay, so this is the data set that we are actually exploring in the notebook. So these are the columns. If you want to see them in Excel, these are the columns under the horsepower. Let's see something. You can see there's a missing value here. There's a missing value here. There's another missing value here. Okay. In Python, pandas specifically, you don't need to do this scrolling to check by yourself. I think in Excel too, you can check the total number of these missing values. So what we're doing was how we do it in actually pandas. Let me unshare this one. We'll see other nice ways of determining the missing values. Okay, but this is maybe a primitive way of doing it. I know 398 rows, but this column horsepower is 392, short of the total, so it means I'm missing value side. Okay, and you can see the same thing here. The count is giving us 392. Each one of them is 398. It means it's only this one which has missing values. But of course, this one, the appearance is a bit messy. We can transpose it. You can do dot T, this capital T. It's only going to turn the table by some angle so let me run it and for us to see so that you can probably read it better. Yeah. So this is all it's going to do. It's just going to bring the statistics on top, counts, mean, standard deviation, and then the columns here. This is how it was before. So the column names are on top, and sometimes I need to scroll like this. I don't really like that idea. So, and sometimes most data that have many columns will be like this, which is time wasting scrolling to read. So you might want to do this dot transpose, and the short is capital T, so dot this. And this is okay. Okay, this is also basically the same thing. So it depends on how you want to read it. So we know that, okay, MPG, the count is this. This is the mean value for the MPG. Standard deviation of this. This is the minimum value at that column. This is the maximum value. And this is 25% of the data, 50%. So this is like 25th percentile. This is the median, and this is the 75th percentile or the upper quartile. So this will be the lower quartile. And you can do the same for all of the other columns. So for cylinder, you can know the mean value, the standard deviation, and this gives you a lot of understanding of how the data is distributed. I told you before that by default, when you call the describe function on the data set, it will give you descriptive statistics only on the numeric columns. If you wanted to do for all of them, well, in this presentation, we did this and it's for the numeric column, and we can do it separately for the non-numeric columns. And this is how you do it. The same describe function, and then you pass this argument. Exclude equals number. What this means is that it should exclude the numeric columns and do it on the remaining other columns, which will be non-numeric. And then you will see it will return this. The origin column, this one, because the summary statistics on non-numeric columns or string columns are different from summary statistics numeric column. So that's why it doesn't merge them. If you do merge them, sometimes it becomes messy. And we have 398 values under that column, and they are unique. The unique values in there are 3. So it's USA, Japan, and Europe. So telling you the unique values there, 3. So 3 countries. And then the top value there is USA. So it means USA cars are more patronized, assuming this is for the company which has sold these cars. Or if you like, US cars are more popular with regards to this particular data set. So that's the top, and it appears 249, the frequency of occurrence, 249 out of the 398. And you can see similar statistics about the name column. It also doesn't have any missing value, but 305 unique values, plenty of them, plenty of them. Means separate car names. So you can have Ford Mustang GL, Ford and 10, Ford another 10, Toyota Corolla, Toyota Camry, Toyota. So you see several varieties of those cars, and they are 305. The most popular car name is Ford Pinto, and it appears 6 times. We have gotten what we are coming to do next already from running this statistics about, okay, I said if you want to kind of merge the two, let me do it here. If you want to merge the two, I can do MPG, so MPGDF, so that both the descriptive statistics on the numeric columns and the non-numeric columns, all of them will come together. If you want to do it like that, this is how you will do it. MPGDF describe. And what I'll do is pass this argument called include. Include equals all. That's all. And this is broken English. Include equals all. And when I run, it will include both the numeric and the non-numeric columns, the scripts. And what I was saying is, Messi, is that because for the numeric columns, we don't have anything like unique, you see this none. This is how pandas represents not available or not a number, like a missing value. Yeah, this is how it officially represents it. So we don't have it for the numerics, but when you scroll, you can see that we have it for the non-numerics. If it is added like this, sometimes it's a bit messy. So if you can kind of do them separately, like the first one, that would be cool. Okay, so like I told you, we already know the unique values in our categorical columns, in our non-numeric columns. Under origin, there are 3 unique values. It means there are 3 countries. We have already gotten it from the describe, but we can do this code to specifically actually do that. This is the column. The origin column. When I do this code, mpgdf square brackets in quotation, square bracket closing, what I'm speaking to pandas is that pandas extract this column, the column called origin, on this data frame, extract it for me. So when I run, you will see this. You will see, okay, from 0 to 397, the various values under for each row. So USA, 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 Europe, USA, USA, a lot of them. See, just remember that we have collapsed the middle. So we are only seeing the top 5 and the last 5. And in between is a lot of values. So you can see US, US, Europe, Europe, and other values there. If the data set is very huge, it will be insane for you to want to count physically. Look, I'm going to count the number of US there. I'm going to count the number of no. So we can do this. We can call this function on this column, dot value counts. Value underscore counts. It's a function. When I run it, it's going to give me the different values. USA is repeating several times. Some other values repeating several times. It's not the repetition that we are interested in. We want the unique values under this column. Bring all of them. Okay, so it will do this and it say, okay, these are the unique values. USA, Japan, Europe, and USA appears 249 times. Japan appears 79 times, Europe is 70 times. So this is also some measure of popularity of the places where the cars are coming from. Maybe something like that. Maybe American cars are more popular for this particular exercise, followed by Japanese cars and so on and so forth. We can do similarly for the name. That is also categorical. So we want to see the separate, the unique values under that column. And then we see it has a lot of values, a lot of unique values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 different car names. But Ford Pinto is appearing 6 times. Maybe that's the most popular car brand, if you like. Toyota follows, AMC Matador follows, Ford Maverick, Chevrolet Chevette, AMC Gremlin, Chevrolet Impala, Peugeot 504, AMC Hornet, Toyota Corona. Okay, so this one is Toyota Corolla. So that's it. Under the name column, these are the various specific car names, 10 of them. We did the value counts on these categorical columns one by one. But of course, we have also learned this looping function. So we can employ it such that we don't need to do this and come and do this. Once we run this simple code, it will do all of that for us. So this is just what it means. We have created a column and a list called cat call, which means categorical columns. You can give it any name which makes sense. And then it's a list of 2 columns, origin and this. And this is the code we want to write. For column, this column refers to any of the values in the cat call. So for column in cat call, you want to come and take this, do something. After that, come and take this and do the same thing. So for column in cat call, column, we are now specifying what should be done. Print mpgd. So we are slicing that column. Then put the column here. So it's going to actually pick this one and come and pick this one. And then it knows that this column refers to this one. So when you put it here, it will first put this one here. And then secondly, it will put this. If you had 1,000 of them, it will pick each one of them. Run the code and do the calculations. That is time saving than you doing this and coming to do this, coming to do this. Of course, if let's say we have 10 columns which we want to do this exercise, we only need to spend time to create this column which contains all the 10 columns and this small code. And then when we run it, it will be doing the job. So when we run it, it will do the same thing. What I only did is that for the first run, when you run this one, the value counts, come and print dashes to separate the second one from the first one. So we'll print these dashes 15 times. Okay, let me make it even. Okay. So when you run, it will do the value counts for the first column, which is origin, and it's saying USA is 249, Japan is this, and then it draws a line and it comes to pick the second column and shows you Ford Pinto, blah, blah, blah. So this is kind of merging the two together. Then we can also check for missing values. All of these things are what we do all of these things are what we do in EDA. Okay, so let's proceed. We are checking for missing values. This function is null. Null, N-U-L-L. Null means something like empty. Is a very powerful function which can help us to actually figure out the missing values in our data sets. So it's now is a function. It's now. The same function can also be called is any. So let me explain. Now is a bit self-explanatory. Now means empty. It's now. So it's like a question. Is it now? And then we have also NA. In Python and specifically in Pandas, NA means something like not available. So which is about equivalent to missing or now. So it's now, it's NA, each of them does the same thing. So when I do is NA or is now, df mpg df dot is NA dot any. It is going to pick all the columns, and then it will tell me if there is a missing value for any of the columns. It will tell me true. If there is no missing value for each of the any of the column, it will tell me false. So when you run this, you will see that it says, oh, it is false, it is false, it is false for MPG cylinders displacement, but it is true for horsepower. It's false for all of the columns, but true for horsepower. And this should not be surprising to you, because when we did, you could see the count that horsepower is 392 instead of 398. And when I even specifically called for the info function, you can see that here horsepower, we have 392. So the difference between 392 and 398 is how much the missing values for that column is. So df dot is NA, or you can also use dot is now, and it does the same thing. So you get the first impression of, okay, which columns do have missing values. So you get true, false kind of feedback, which is good. Then you can run this, but of course you can skip this one. It's just for tutorial, so we have to bring all of these things. You can skip the first one and run this one through. mpdf mpgdf dot is now or dot is NA. I actually prefer the NA. Dot is NA dot sum. If I run the dot sum on this, it's going to bring each column, and then for each column, the sum of the missing values or the total missing values. So you'll see that it is saying, let me run. It's saying that for MPG, we have 0 missing values. For cylinders, 0. All of them 0, but for horsepower, we have 6 missing values. And then we need to decide on how we deal with the missing values. We can deal with the missing values by 3 main ways, or maybe more. The first one is that we can drop the missing values, and we take this approach when, let's say, for this particular, let me use this particular data set. We have close to 400 rows. And then the missing values here will affect only 6 rows. So if you compare the size of the data overall, and if you have to drop the missing values, 6 of them, you might conclude that, oh, it will not actually change what the data represents. Just 6 rows which are deleted. And if that is the conclusion, maybe the data size is even more than 400, maybe 1,000. I was telling you some data set we just worked with about 8 million. 8 million, if you're deleting just 6 rows out of 8 million rows, it will not really change anything about what you will see from the data. But if the data set is maybe small and already it is shaky about what you can actually glean from that small data size, then it will be very expensive for you to drop. Okay. If you want to drop, how would you do it? You just say mpg. I will not run that code. I'm just speaking it because when I run, it will be, and I don't want to go back and rerun all the codes from top. You can just say mpgdf dot drop NA. like this. This is the data frame, mpg underscore df. Then I call this function dot drop any. Drop any is a function which can make you drop missing values. That's why I said I prefer to use the is any because it's so much connected with the drop any. We don't have drop now. Okay. So mpgdf dot drop any. That's it. And it will drop every missing value from the data set. The data set will reduce by the size of the missing values. For this particular presentation, we will not drop any. This is an exercise I'm giving to you. For the same data sets or any other data sets, create a copy, keep the original somewhere and create a copy of it. And then in the copied version, if you don't even have missing value issue in the data set, intentionally delete some of the values to artificially create missing value situation and save. And when you are reading, pandas will automatically tell you that these are missing values in this column. Then use this function, the object's name dot drop any, and kind of see the data again and see the effect of it. Okay, so that's an exercise for you. We are going to go by the imputation approach in dealing with missing values. The imputation, so let me talk about it here. Let me run this so you can see it well. Treating missing values, I've talked about the dropping of the rows. And this approach might be reasonable if the rows that will be affected if you drop is few and the data is very huge. You can drop if you think it will not make any difference. You might also want to drop the column, the whole of the column, if you can see that one particular column. That's where the missing, for example, in this case, the horsepower. If you can see that, oh, the horsepower column, almost every row that matches that column, there's a missing value, plenty of them. And then additional consideration is that, does that column matter? Maybe that column will not matter so much about the kind of work you want to do, the kind of statistics modeling you want to do. In that case, you can drop the column. Yes. And if you want to drop the column, let me, it's still the same mpgdf.drop any. But this time around, you specify the axis. Axis equals 1, that is for column. By default, it will drop the rows and keep the column. So you don't even, the row deletion is the default. So that's why we don't pass anything. Okay. We didn't drop any. And we can't keep any there like that. So we need to do something about it. There are several methods of imputing missing values. You can impute the missing value. Imputing is like kind of calculating it by some logical, reasonable way. And these are some of the ways. We can impute it by just replacing that value there with some value. So maybe we have looked, okay, let's replace it with maybe 10. Let's replace it with maybe 5. Just some constant value that comes into your head because that's what you do for whatever reason. That is up to you. So that's one way you can do it. And you can simply do that by saying mpg df. If you want to do it for the whole of the data set, mpg df dot fill any. Let me put it here for you to see. And you have to put this thing down in your book because you have to go and practice on them. So that will be, in our case, MPG DF dot, there's a function that can help you fill missing values. The one that can help you drop missing values is called drop any. We have talked about it. The one that helps you to fill missing values is called fill any. Then that constant value that I want to fill the missing spaces with, let's say 10, I put it here, and it will fill every missing space with a 10. If that is what makes sense for you, that's how you do it. But in most cases, this is not too intelligent because the columns have, the column values are informed by certain dimensions. And therefore, you cannot do that kind of one size fits all kind of solution. So what normally for numeric columns we do is to fill the missing value under that column with the mean value of the column. The mean value of the column. The idea is that, and of course, even before that, I don't want us to go into that deep statistics. Even before going by that approach, you might want to first of all see the distribution of that column. And if that column is a bit more normally distributed, then there are certain properties around normal distribution which you can employ. What it basically means is that, okay, most of the values are just around the mean in the center. So the mean is a representation of the values, and therefore you can use the mean to fill the missing value. That may not, or that may be disputed if you check the distribution of the column and it is highly skewed, then the mean might not be a representative value. So maybe something else, maybe the median in that case can be used. In that case, I'm just assuming we have checked and everything is okay, it's kind of follows, it's more normal than non-normal. So we are going to fill it with the mean value of the column. And what you do is that column, MPGDF, horsepower, that's where we have the missing value, 6 of them. Set that column to what this will return. So this side of the code is saying that this MPGDF horsepower, this column, fill it, not fill any, fill it with the mean of that column. And the mean of that column is MPG df horsepower dot mean. This is quite simple to understand. Replace the original column. So that's the meaning of MPG horsepower, this part. We are going to set this column. In other words, we are going to replace this column, which is already in the data frame, with this computation. MPGDF horsepower dot fill NA with the mean values of the column. And when we run, it is going to fill the values, the missing values, the 6 of them. And now, if we do that, after doing that, we can now check that column for missing values. So this is the column. So when I do dot is NA and call the sum function, it should give me the sum of the missing values. And it says 0. And now if you even want to call the info function, you can do mpg df dot info. And now we can see that for the horsepower, oh no, so it's still there. So let me run it. It means we have not run this one. So when we run this and run this, okay, and run this again, now let's check. you will see that the missing value situation for the horsepower is now gone. So we now have 398, just like any other column. And the six spaces which were previously missing are now replaced with the mean score of the values under the horsepower. That's basically what it means. Okay, so we are done with a lot of the aspects of exploratory data analysis. This is the part that we have done is more about the physical nature of data sets. Columns in it, rows in it, missing values, dealing with missing values, blah, 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 blah. And now we want to understand trends, patterns. That is the next part of the analysis. We do this part basically in two stages: univariate analysis and multivariate analysis. It sounds a big word, but it is very simple. Uni is one. So univariate is like, okay, for each of the columns, we want to get some understanding. So that is the univariate analysis, column by column, variable by variable. And the multivariate usually will reduce to bivariate. Okay, so between MPG and cylinder, what can we understand? How do the two go together? That is within the realms of multivariate analysis, or in this case, to be very specific, bivariate. So basically, that's what that part is about. So let's do univariate analysis, checking for how the various column data are distributed. Mostly the univariate is about the distribution of the data. That's the best of what we can understand about single column. What is the distribution of the data in that column? That can give us a lot of information, at least about what model we can do on such data with such distribution, or whether we have to do some modifications on the distribution, for example, logging the data to force it to be normalized. A whole lot of things go in there. When you're doing statistics next semester, do well to connect this to your statistics and ask your teacher meaningful questions for understanding. So this part is basically visualization. They are not kind of numeric quantities like the describe function, numbers to understand. These are pictures to understand. So we want to understand the distribution of each of the columns. So let's start with the numeric column, MPG. In Seaborn, you can use any of the plotting packages to do it. We are using Seaborn. It doesn't mean that's the only package you can use. You can use Matplotlib to do it. And you can even use pandas on plotting function to do that. So what we are doing here is that in Seaborn, there is a plot function called displot, DIS plot, which means distribution plot. And there is also hist plot, which is histogram. You can see this is histogram. The only difference is that I'm actually adding this to it. So we are going to do this plot for distribution plots. What the arguments are is that the data for our case is MPG DF. And then because this is univariate, we only need this one, the X parameter. Or we need one, either X or Y. Because this is single column by single column analysis. So X is equal to MPG. When we do this, it will give us the distribution of the data. let me show you. Let me unshare this and share something. Let me share the spreadsheet itself to you so that you get the understanding. Okay, so this is the spreadsheet, and we are here in the MPG column. You can see so many values. This is where we are. You can see so many values here. When you use your eyes to see these values, it will be very difficult for you to get any sense of how the data is distributed. That is where visualization becomes very powerful. So these values under this column, how do they show up? What is the picture like? How are they distributed? Where do we have most of the data concentrated? Where do we have most of the data concentrated? Are most of the data concentrated within this range of numbers, maybe middle numbers, or higher numbers or lower numbers? If most of the data are concentrated in the middle, then the data will be approximating the normal curve. You will get to understand it better in your statistics, or you can read further on it. The shape will be more bell-like. I'll show you later. If much of the data, majority of the data are low values, they are small values, then you will see that the data will be much more concentrated around the smaller values, and it will be skewed to the right. And if you have much of the values in this column being bigger values than smaller values, then you will see that the concentration of the data will be in the higher value regions, and the data will be skewed to the left. That is the distribution. You cannot really use your eyes to gauge that by just looking at the values here as I'm showing you. So let's go back. Okay, so we are back. So you can see when we do sns.displots, we pass our data, and then the x variable, which is mpg. KD is equal to true. This argument is only bringing this line, this line, so that it can help us gauge the normality of the distribution very well. Okay, so that's what the KD stands for, Kelvin density estimate. You can check it. You can check what KD stands for. So this is the distribution. You can see that for this particular data column, we have, this is the low values. Let me show you. This is 0, 10, 15. So it starts from 0. These are where the low values. And then it's telling you, oh, for 10, for cars with MPG of 10, this is the size. They are just below about 9 or so. They are not even up to 10. And then from, let's say, about 11 or 12 up to about 35. This is where, so the MPG values from 12 to 35. This is where most of the cars' MPGs are. Most of the cars' MPG values fall between, let's say, 12, assuming this mark is 12, to about, let's say, if this is the cutoff, let's say 30 something. So that's a very beautiful thing. You couldn't have seen this thing from just reading the digits. And of course, we can even do another one. Let me do it here. We can do SNS dot violin plot Bowling plots can also help us to see the same shape of the data, the same distribution of the data, but maybe in a way to make us understand it or even confirm this one. So violin plot, because it looks like violin, and it's also a plot that is used to gauge or measure the distribution of the column or the data set. So it takes the same input data equals, in our case, MPG, DF, and then X equals MPG. So this is the violin plot. It's doing the same job as the first one we have done. It's kind of helping you to gauge where we have our data concentrated. In other words, how the data is actually distributed. Then you can see that, okay, much of the data, you see where the violin plot is swollen, that is where the concentration is. So you can see that, okay, around here, almost nothing is here, but from this size going up to, let's say here, the data is big, especially within this region. So most of the cars have the NPGs around this size. Let's say, assuming this is 18. So most of the cars have their MPGs 18 because this is where you have the biggest, this is where most of the distribution is. And this is the same thing that this guy is saying around here. That's the same thing. Yeah. So that's about distribution. And you can do, of course, these are not the only plots that you can use to find the distribution of the columns of the data sets. There are other beautiful uh, plots or graphs you just need to learn. You should be inquisitive enough to. So you have to do this for all of the columns to get an idea of the distribution of the data in that column. And statistically, that is going to help you to decide whether you need to kind of manipulate the data in some way to fit some analysis you want to run, or most appropriately, find a statistical method which better suits the distribution of the data. It's very important. Okay, so let's see box plots. Box plots can also help us to find the distribution, but in addition, not exactly the distribution, in addition to the distribution, it can also give us information, outliers, and some other information. When you read about box plots, the literature has it that it's a statistical tool which kind of gives you measures on five key statistical measures. You can get the minimum value, maximum value, you can get the lower quartile, upper quartile, and therefore the interquartile range. You can get the median, and you can also see if there are outliers in the data. So for example, if I want to do, if I want to check whether there are outliers in the MPG column data, and also check the minimum and the maximum values and the median, I can use the box plot. The box plot is quite very informative. So read more about it in terms of how you use it in your data analysis is very, very informative. So if I'm doing it for the MPG data, I'll just do sns.boxplot. The data is our MPG D, and then we're going to do it on the MPG column. So MPG. Okay, so this is the box plot for that column. And it's telling you, okay, the minimum value in that distribution is about 10 or a little below 10, around here, let's say 9 or so. You can go and check, but at least this gives you the bigger picture. And this is the 25th percentile or the lower quartile. This one, this middle line in the box is the median. And this is the 75th percentile upper quartile. This is the maximum value in the data sets. And then this dot here is an outlier. So there is some extreme value which falls outside of what is seen to be normal. But I think this is just one value. It's quite revealing. But of course, we can save time, or not even save time. This is MPG, box plot for the MPG column. You remember that in our data, we have 3 sources, or if you like, if you check the origin column, we have 3 places. The cars are coming from either USA, Japan, or Europe. So we may want to see how the MPG is distributed for the cars, factoring in or bringing into the equation where the cars are coming from. So even with this one, with this volume plot as we have done, and even with this plot as we have done, we can do that kind of thing. Let's try it on the volume plot and see. When I pass y-axis, and I say the y, if I say the y should be equal to the origin, or if I can swap, it doesn't matter. But let me put the y to the origin and let's see what we will see. Origin. What this one is going to do is that it's going to put the origin here. So we'll have USA, Japan, Europe, somewhere here. And then it's going to do this plots inside here across this value. So what it's going to do is that it's going to split the plot for each of the origins, whether USA or Japan or that. Okay. So we can see this, that if we factor in where the cars are coming from, then we can even get more revealing information. So if you look at the distribution of MPG for USA cars, they are like, okay, most of them, if you want to gauge it from here, maybe majority of them will be between here. Let's see, this is where most of them start here, and it will probably, let's say, end somewhere. If you want to bring it here. Okay. So the USA cars, the MPGs are relatively smaller. That's according to the data. And then the Japanese cars, this is where the concentrations are. The concentrations is a higher number. So 30, or if you want to even pick it from here, so that will be between 20 and 40. 20 and 40 MPGs. And Europe cars are also between, let's say, if you like, 20 and maybe 35, thereabout. Yeah. And you're able to do all of these things just with one code. And in fact, there's no way you can do this with your calculators and your pens that you bring to class. There's no way you can get this information from a data if it is given to you. Yeah. So that's about distributions and then outliers. And for the box plot, we can even do the same thing. So if you look at this code, box plots on MPG, but we are factoring in the origin so that you can say, okay, the box plot for the MPG based on where the cars are coming from. So you can see that, okay, USA cars, it confirms the earlier discussion. The concentration of it is within a lower number. It means their MPGs are quite relatively smaller. But of course, we have outliers, two of them. For the Japanese cars, you can see where the concentration of the data is falling, just speaking the same language as the Berlin plot is speaking. But we also have one outlier, but we seem to have a lot of outliers coming from European cars in terms of the MPG. Okay, so that's about the box plots and the Berlin. For the categorical columns like the origin, we can also check the distribution using a count plot, let's say a bar plot like this. Okay, so when we do SNS.count plot, so that is how Seaborn does bar plot, count plot. Then you pass MPG data as this data frame X is origin. Then it's going to tell you how many cars. Okay, so under that column, under the origin column, it's only going to show you how many of the entries in that column are for USA. So 240 something. I think we saw it somewhere else. And then how many cars are for Japan? This is it, and then Europe, and that's what. Okay. So you do similarly for the other one. Just that the other one, we have a lot of separate values, about 10 of them. So if you do a count plot, you see a lot of tiny bars, and it's not quite informative. Yeah. So this is a gist about univariate analysis. You can learn further on that. So let's talk something small about bivariates, if you like multivariate analysis. Then we can close the lecture. So what we mean by multivariate analysis is that, so let me intentionally call the data frame here, mpg dot info. So this is the data set. We have mpg column, cylinders column, displacement, horsepower, weight, acceleration, model year, origin, blah, blah. We want to understand the relationship amongst these columns. We can have a handy way of doing that by using Seaborn's pair plot. So what pair plot is going to do is that, well, before the pair plot, we can use numerical quantities to get an understanding of the relationships among various columns. And of course, the basic one you know is correlation coefficients. So we can compute the correlation coefficients amongst all of them, the numerical. And then we will check this against this and understand how they are moving, how this variable is moving together with this. Are they moving in the same direction? Do they even seem to move in a determinable direction? And what's the direction like? They are moving in the same direction. They are moving in opposite directions. They are not moving in any direction. They don't seem to communicate. That is the understanding we want to get from that multivariate analysis. Okay. So we can do correlation matrix. That is multivariate analysis, correlation matrix, and it's very simple to do that. We can do MPGDF dot correlation, and this is how Pandas does it. The function's name is call, and it will bring the correlation matrix on for the numeric columns for us. So you see MPG cylinders, all the columns, numerical columns at the top, and the same thing as columns and the same thing as rows. So that's the matrix. And then we can see where a column meets another column. So that's the coefficients of correlation between the two variables. Correlation coefficient between a variable and itself is not what we are looking for. So nicely, this matrix will show that one as the diagonal, leading diagonal. So it will be 1, 1, 1, 1, 1. And this is like a mirror. So the upper part is the same as the lower part. So you can read it only from the lower part. It's the same thing you read from the upper part. So when we check MPG against cylinders, MPG here, cylinders here, the correlation is negative 0.77, which is not a bad number at all. MPG against displacement, the correlation is 0.8, about 80%. Horsepower, 77%. Weight, 83%. Acceleration, about 42%. Model years, and you can check for the other ones. So that's how you read it. And the correlation coefficients speak to tell you, oh, okay, this is how these two variables happen to relate with themselves. The relationship can be causal or it may not be causal. At this point, correlation is only establishing that there is a relationship. Whether the relationship is a causal one or not, it's not a job of correlation coefficients. We will need further statistics to confirm whether the relationship is a causal one or not. Okay, so there's a nice way we can visualize, we can see this correlation matrix. And then there is something in Seaborn called heat map. So we can use heat map, we can convert the correlation matrix as we have seen there with, convert it to a heat map. The only difference is that it's going to convert it to something like a graph with some color coding so that it can be very easy for you to isolate what you want. So let's see how we will do that. We have already done the call. If you want to save the correlation matrix as some name, fine. Then because we will need the correlation matrix into the heat map. Or you can write this full code inside the heat map automatically. So let's do it straight away. So we are going to do sns.heatmap. And heatmap take arguments including this one, the correlation matrix. So if you had already saved it, then you bring that object name here. We didn't save it, so we have to do it fresh. Or let me break it. So let's save this as an object. So let's call this correlation matrix. So let me just call it format. So that's correlation matrix. So in the heat map, I need the correlation matrix. I have called it format. And then the most important thing is that I need to pass this argument, annotation. So the short form is annots. So annots equals true. What that is going to do is that it's going to put some markers and with some scale for you to read the colors, what this color range means, and so on and so forth. Okay. So you get something. I think I have a bit of a problem with my notebook. It's supposed to show you all the numbers in the grid. Yeah, but quite recently I've seen that it only shows just the first row or so. Maybe I'll have to reinstall and reinstall the Anaconda. So sorry about that. But what it's supposed to do is that it's supposed to, as you see here, 1, 0 point, you can check it with the matrix. So this is the matrix. Let me call the matrix here. The matrix is called math. Okay. So MPG, you can see one here. This is this one. So this is MPG, and then down here is MPG. And then MPG against cylinders is 0.78. MPG cylinder 0.0. Let me see. This is MPG. And here is cylinders 0.78. Okay, this one is converting to 2 decimal places. So you can see MPG and cylinders is approximately 0.78. So it is converting these numbers, actually kind of color coding the numbers, making it a bit more beautiful for your eyes to read. That's what a heat map does. Sorry about the fact that it didn't show. It's supposed to show at your side. It will show for all of these things. This has to do with my machine specifically. So that's the heat map, and that is also for multivariate analysis. Then we can also do, in support of this, almost all of them are trying to give you information about the same thing, but maybe in different ways that makes life more easier for you. You can do pair plots, which also tries to convert this correlation matrix into scatter diagram matrix, sort of. So let's do SNS dot pair plots. And pair plot has to take the whole data because it's going to do that kind of thing for all the data. So MPG DF. And because it's going to do that kind of exercise on the whole data set, depending on the size of the data set, it will take some time. Okay. So this is the same as these numbers, but in graphs. So the leading diagonal, where we have the column against itself, pair plot represents it with the distribution of that data set. So this is the distribution of the MPG data set. This is the distribution of the cylinder data set. This is the distribution of the displacement data set. And that gives you an information about whether the data distribution is okay, something is to be done about it, or based on how it is, which statistical method is more suitable, and so on and so forth. So that gives you the distribution for each of the column. And then the upper part is the same as the lower part. It's a correlation matrix, just as it's in the graph. So this is the correlation, or this is the scatter diagram between, for this one here. This one will be between cylinders and MPG. So cylinders and MPG, this is the picture about the correlation in a scatter diagram. For the rest, you can see some nice other things. If you want to make it a bit more fancy, not really fancy, for example, and of course it will be a little bit clumsy. If you want to see how these distributions, as we see them, are separated by, for example, the origin of the cars, US, Japan, or or what do we call it, Europe. Just like we did for this one here. We wanted this box plot to be separated. This box plot is the bigger one for the whole data distribution. Whether that MPG is for a car in the US, a car in Japan, or not, it's for all of them put together. So if you want to kind of show a separation by the origin, this is the code we did, and it's showing them. Similarly, we can also show a separation of, because this whole data set, as you see them for each of the plots, is for the whole of the data set, which is a mixture of cars from Japan, cars from US, cars from elsewhere. So you want to pass that kind of separation argument that is called a hue. So we can do hue equals true. No, hue equals what the separation variable. In this case, origin. Okay. So what it is only going to do is that it's going to, for example, here, this whole points are for all of the cars from every origin, but it's going to show the dots based on where they come from. So it's basically going to do the same thing again, just it's going to show different colors for different origins. Yeah, something like this. And it can be very informative. For example, if you look at the distribution of the cylinders, the distribution of the cylinders for what does this color represent? Okay, so this is the legend. The orange one is Japan. So the distribution of the cylinder values for Japan cars is quite normally distributed, if you see it. And even if you check for MPG to the green one is almost very normal, and the green is 0. If you check here, Japan car distribution are approximately normal, and so you can get all of these things to be what is inside the data. This one, your eyes cannot look at the data and see. It has to pass through the software. Yeah. So these plus some other things are what you have to do inside exploratory data analysis ahead of building some predictive model. So at this point, I want to pause. I have talked plenty, and I want you to also talk some. So you can unmute yourselves, and you can join the lecture in terms of a question or some contribution that you. So the floor is open for that session. Any questions, please?
No, sir.
Okay, so nice, no questions. It means we have closed the session. We will do the second version of it where we build on this to do some predictive model later. Thank you very much.
Oh, you're welcome, sir. Thank you too.
Yeah, thank you, sir. Good night, sir.
Thanks, sir.
Good night.